Hello everyone. In this video I am going to go over some questions about chi-squared test for independence and linear regression. So here is my little procedure table that I will give you guys to do your chi-squared test for independence. And normally this test is done in Excel, but for paper type questions to be done on paper, then I will just give you the p-value that you would normally calculate yourself at this point. But I will still ask you to do this part where you fill in the expected table because you can use a calculator to do that. Okay, so let's look at the first question here. A random sample of 100 American movies from 2022, were categorized by genre and release size. The results are shown in the table below. Perform a chi-squared test for independence to answer the question, is there enough evidence to conclude that genre and release size are not independent? Okay, so first of all, I usually like to look at this and just see myself if I think they're independent. So looking at the proportions here, 31 and 69 of wide and limited, it looks like usually about twice as many limited as wide. So like this is twice of this one, which looks kind of close here. 5 times 2 is 10. It's not far from 7. 14 times 2 is 28. That's not far from 32. 1 times 2 is 2. That's pretty far from 18. So this row is suspicious to me. 11 times 2 is 22. That's pretty far from 12. So already I'm thinking these don't look real independent to me. I think they might be dependent or not independent. So I'm expecting kind of small-ish p-value, but let's see how it goes. All right, so does the sample data pass the assumption for the chi-squared test for independence? So the only assumption that we check ourselves is that it's a random sample. There's another kind of hidden assumption down here. This check that you do at step 4 is about making sure that the thing that is supposed to have a chi-squared distribution would actually have one close enough to a chi-squared distribution, and that is the sum of squared errors that Excel kind of calculates in the background for us. That's what that is about, but we don't explicitly check that at the beginning because you can't check it until you've calculated it. Okay, so random sample is what I'm looking for, and I see it was a random sample, and I remember sampling this myself in 2022, so I know it actually was a random sample. Okay, so this is ES. What is the alternative hypothesis for the test? So the thing that you are trying to prove is given in the question, and for chi-squared test for independence, it can only be just that the, that the two qualitative variables are not independent. And in terms of this exact question, it is that genre and release size are not independent. So I'm just going to paste that. Genre and release size are not independent. Then for your null hypothesis, it's always the opposite of your alternative. So maybe I can spell that correctly, that they are independent. Okay, and now we're going to fill in what these table entries would be if these two variables of genre and release size were perfectly independent, meaning that we're going to mimic this exact ratio of 31 to 69 in each of these rows here, but making it add up to the right row total over here. And so the way you do that is using this formula, row total times column total, divide by table total. So we're going to have to do that 8 times. We're going to do this column total times row total, divide by table total. Okay, and I'm going to put these in all of these cells. So I'll just do a couple to show you, and then I'll just fast forward through the rest of them. So 31, actually maybe I will type them in these cells so you guys can actually see what I'm going to do. So this is going to be 31 times 12 over 100. This is going to be 31 times 46 over 100. This is 31 times 19 over 100. 31 times 23 over 100. And then same way over here, except I'm just going to be really lazy. Change these 31s to 69s. Okay, so this will be 69 times 12, 69 times 46, 69 times 19, 69 times 23, and then these are all divided by 100. Okay, so I'm just going to, if I'm doing this on paper, I'm just going to take my calculator, I'm going to do 31 times 12, divide by 100, no parentheses needed, so it's 3.72, 31 times 46, divide by 100, 14.26, And then I'm just going to pause and do the rest of these so you guys don't have to watch me punch buttons over and over. Okay, so these are the numbers that I got. And at this point, again, I like to kind of like usually compare it to my original table and see, are these numbers similar? Are they pretty far off? What do they look like? So I'm looking at like 5 versus 3.72, 14 versus 14.26. That's not too far off. 1 versus almost 6. That's not real close to me. 18 versus 13. I'm getting a little further off now. 7 versus 11. 12 versus 16. So yeah, they're a bit off. They're not super far off. So I'm not sure what kind of p-value I'm going to get. Maybe one that's like borderline. Okay, but let's see. Is any entry less than 5? Yes, actually this one is. That is less than 5. So at this point, that means that I cannot trust that when this sort of background calculation goes on where you do the top table minus the bottom table, square all the entries and add them up, I cannot guarantee that that is going to have the right kind of distribution to make this test valid. So I'm actually going to stop right here. And I'm not going to do the test. All right. So that's it for this one. I do kind of ask you guys, like, if it's on a testing situation, usually I tell you to just keep going. Just in case, yeah, like right here, just in case that you were wrong and you could get partial credit. But for this one, I said stop if it's less than 5. So we will stop. All right, next one. A random sample of 100 American colleges were categorized by type, public or private, and region, Eastern or Western. The results are shown in the table below. Perform a chi-squared test for independence to answer the question, is there enough evidence to conclude that college type and region are not independent? Okay, so does this pass the assumption? Is it a random sample? Yes, it was. And I really sampled this myself. I think I used the college scorecard data from US Department of Education. Yes, random sample. What is the alternative hypothesis for the test? So it's that college type and region are not independent. So the null hypothesis then is going to be that they are independent. So the opposite of the alternative. Now I'm going to fill my table. So I'm going to do, this will be 46. Oh, I'm sorry. I was looking at this number. It's this one, 70 times 64. Divide by 100. This is going to be 70 times 36, divide by 100. This is going to be 30 times 64, divide by 100. Oh, I forgot to do the thing where I like make my own judgment of whether I think it's independent. But let's just see how the test turns out in this case. Okay, so now I'm going to put these in a calculator. Okay, so here's what I got. And I'm looking at my original values here, my real values, and my expected values for what they would be if the variables were perfectly independent. And I'm seeing, yeah, these are really close together, like 46 versus 44.8, and super close together. So I'm thinking these variables, I'm not going to be able to show that they're not independent. I think they probably are independent. Although we also can't show that because the way that hypothesis testing works, you cannot verify the alternative hypothesis unless you reject the null hypothesis. So vice versa is also true. If you wanted to verify the null hypothesis, you would have to reject the alternative hypothesis, but we don't have a way of doing that. Like the test is not set up in a way that we can calculate probabilities associated with that. Okay, so anyway, is any entry less than 5? No, so we're good to keep going. All right, assuming the p-value is 0.5890, and that's from Excel because we're doing this test without Excel, write an interpretation statement. So this is a really high p-value. P-values only go between 0 and 1, so this is very high. Anything over 5% or 0.05 I would say is high. There's some debate amongst scientists over like whether 5% is low enough to reject the null hypothesis. Some people want it much lower, but it's really field dependent. It depends on your field of study. So my interpretation here, I'm going to go back to my table, procedure table. When p is not very small, with a p-value of whatever it was, we do not have enough evidence to conclude that, and then put your alternative hypothesis. Okay, so I'm going to do, oh, sorry, wrong place. I'm going to do, so first of all, this was no. And now I'm going to say with a p-value of 0.5890, there is not enough evidence to conclude that my alternative hypothesis, college type and region, are not independent. Okay, one more of these. A random sample of 100 American colleges were categorized by type, public or private, and selectiveness, high, medium, or low, based on admissions rate. The results are in the table below. Perform a chi-square test for independence to answer the question, is there enough evidence to conclude that college type and selectiveness are not independent? I'm going to go ahead and grab that and put that in my alternative hypothesis. Oops, sorry, control. Yep. And we make that blue. All right, and so the answer to this first part, this is the same data set, so this is a yes. And I did sample it myself, and I really did it randomly, I promise you. Although what exactly is meant by 100 American colleges is a bit oblique, since I first eliminated a lot of things like seminaries and beauty schools and acting colleges and things like that. So there's some complicated processes that are summarized by very short text here. Anyway, but I really did do it randomly. So college type and selectiveness are not independent. That's what we're trying to show. So for our null hypothesis, we're going to suppose that they are independent and see what that would look like. So now we need to fill in what this table would be if the two variables were perfectly independent. So once again, we're just doing the two totals, divide by the table total. Here I made it 100 just to like help you guys out. Easier calculations. Oh, these are both 54. That's weird. Okay, so 54 times 35 divided by 100, and then I'm just going to pause and speed this up. Okay, so here are the numbers that I got. I'm looking at my real numbers, and I'm kind of comparing to these ones. So I guess the main thing here was that the totals of public and private were very similar, almost half and half. So these should be half and half, almost the same in each cell, but they're kind of not. Medium is more skewed towards private. Low is more skewed towards public. High is more skewed towards private. I don't know if those are enough different to make a low p-value, but let's see. So is any entry less than 5? No, although this one is so close that I'm wondering if I actually fudged the numbers to make it come out above 5. I don't remember. That sounds like something I might have done. All right, assuming the p-value is 0.0180, write an interpretation statement. Okay, so this is a pretty low p-value, 1%. So this is the probability that if the null hypothesis was true, if college type and selectiveness were really independent, this is the probability that our real numbers up here would be as different from these ones down here as they are. So was it just random sampling that made these so far off from these ones? Well, there's only a 1% chance that they really are independent, and we just happen to get these not independent looking. So since there's only a 1% chance, I think it's unlikely. So I'm going to reject the null hypothesis, and I'll put this in the low p-value interpretation, which is up here, with a p-value of whatever it was. There is, I'd say this is, I wouldn't call this strong. I'd say there's some, but it's a bit up to your point of view and your field, so I don't want to teach you guys one hard and fast way of doing it. If you remember a sense of uncertainty and how do I interpret this again, I mean, that's fine with me because that's the reality of the situation. So with a p-value of 0.0180, there is some evidence to conclude that college type and selectiveness are not independent. It's kind of what we would expect. Actually, the more selective colleges are more frequently private colleges, like your Ivy Leagues, your Harvards, your Yales, and so on. Although there are some very selective public colleges too. All right, now we're going to do some linear regressions. So a linear regression analysis was done of all movies released in American theaters in 2022 using the number of theaters the movies opened in and the maximum number of theaters the movies played in. So here's the picture. So theaters opened in, and then the max theaters. Usually, like, some movies will do a release schedule where, like, they'll open in just like in Hollywood and New York for maybe a week, and the critics watch it, and then they release it to the rest of the country, kind of thing. So that's these points that you're seeing here. And then you might also have situations where, like, a movie just unexpectedly was more popular than they thought. So, like, these three ones that are up here are probably some kind of Goldilocks situation where, like, oh, we thought it was just not that great, but actually people love it, so we put it in more theaters. And then hopefully there aren't too many where it actually went down. All right. No, I guess that would be impossible. It's impossible for the max to be less than the initial, right? Because the initial number is included in the numbers that you're taking the max of. Okay, yes, I know math. I have a PhD in math. All right. What does the R-squared value tell you about the strength of the linear relationship between the variables? So I put the little cheat like variables here for you guys so you don't have to memorize them. But the R-squared here we have is 0.94. It's extremely strong relationship. Very strong, extremely strong, I would say. So I'm going to select that one, highlight that one. Okay. Use the regression equation to predict the maximum number of theaters for a movie that opened in 1,000 theaters. So basically the prediction is like, it probably won't go to much more than 1,000, right? That's what I'm seeing from the data here. Like maybe once in a while, but most likely it'll just stay like right near 1,000. But I'm going to use this formula here, the 0.9744x plus 111.32. That is what I'm going to use for my prediction. I'm going to plug in the x value of 1,000. Okay, so I'm doing y equals 0.9744. And now for x, I'm going to plug in 1,000 because that's this number here, 1,000 theaters. That's the meaning of x, number of theaters that it opened in. Okay, and I'm going to add my intercept, 111.32. And now I'm just going to grab a calculator and 0.9744 times 1,000 plus 111.2. Okay, 1,085.72. Right, so that is my prediction. It's not much more than 1,000, just a few more. Number 5, a linear regression analysis was done of all movies released in American theaters. This is bugging me. Let me put this over here. In 2022, using the domestic box office and the international box office. And the results are shown over here. What does the R-squared value tell you about the strength of the linear relationship? So not as strong of a relationship this time, but it's still pretty strong. So this is in the very strong category, not as high as the last one though. Use the regression equation to predict the international box office for a movie with a $200,000 domestic box office. So 200,000 domestic on my X. So I'm looking at right here, like this point on the, this point on the chart. So it looks like the prediction should be about maybe like 250, so like halfway to 300, which is halfway. Okay, so I'm going to use the equation. Y equals 1.3979. My X value is 200,000. No, I'm sorry, 200 million. What am I saying? These are millions. 200 million plus 227802. All right, now I'm going to get calculator. 1.3979 times 2, 1, 2, 3, 4, 5, 6, 7, 8. Yeah. And I'm going to add 22702. Okay, there we go. 279,807,802. And again, if you check against your little red dashed line here, it should look about like the y value is in the right spot there for being on this red line. Okay, last one. Oh, that was the last one. All right, well, that wraps up this review video. And if you have any questions, send me an email or come to office hours. See you later.